Go. Welcome, dear students, and welcome to Vista's V-Learning, an online educational platform. My name is Denzil, your physics tutor for class 11. So let's get started with our session. Today's session is based on the chapter measurement, which happens to be the session 4. And today's discussion will be based on significant figures. The previous session, we left off with measuring errors in a given instrument. So let me continue with few more concepts of errors, and then we can begin with significant figures. So let us have a look into the different types of errors based on the combination of errors. And when do the combination of errors arise? Here's a given experiment. Let's say a circle, which is shown on my left hand side and on your right hand side. This circle has a certain length, which is the boundary called the circumference of the circle. The measure of the circumference of this circle can be done by theoretical procedure where you write C is equals to 2 pi r. But practically, can you measure this circle? What will you do, or how will you identify this length of a boundary of circle? Take a guess. Well, one way you can find this length is by using a thread. That's right. You use a piece of thread. You will trace the path of the circumference using the thread. You will measure how much of that thread measures the boundary of that circle. Once you have acquired that particular length of the thread, you can compare its length with the standard scale. And this scale will give you an approximated value of what is the measure of a circumference of a circle. Now, I'm giving you an approximation. That is because the true value cannot be identified using just a piece of thread and a ruler which has a least count of 0.1 centimeter. Since the resolution of our scale is less, where we're restricted to 0.1 centimeter, we do not get the true value of the circumference of a circle. So which means there are certain errors which arises out of this measurement. Now, apart from this measurement for a circle, we also have measurement for different physical quantities, and one such example is to identify density, where density is defined as the ratio of mass by volume. So here you have to measure two other factors to identify density, that are mass and volume. Now, while measuring mass, obviously the instrument that you'll be using has a resolution. So which means there will be an error for a given mass. Similarly, for a volume also, when you measure a volume, there will also be an error. So if there are error in two different measurements such as mass and volume, how will you identify the total error? Error by mass, error by volume, what will be the total error by density? This is where we discuss the combination of errors. So now let us look into the different combination of errors. The first combination of an error is called the sum or difference. So how does it operate for a sum or a difference? Suppose, let us consider two physical quantities A and B. Let us consider two physical quantities A and B, each of which physical quantity has its own error. A has an error which is given by A plus or minus delta A, where delta A represents the absolute error. As well as physical quantity B has its error, where it can be represented by B plus or minus delta B, where delta B is called the absolute error. So one more time, what is delta A and delta B? What are they called? Delta A and delta B are called absolute error. Now, since we are trying to add or subtract these two quantities, let us stick to first part, which is adding the two physical quantity. While you have to add two physical quantity, you get new quantity in return. So let us call that new quantity as Z, where Z equals to A plus B. Now what do we know is that A has a certain error, B also has a certain error. So let us solve that by writing the total error, the total physical quantity Z with its respective error given by plus or minus delta Z. See what I've done here? I've written delta Z, which represents the total error by combination of the other two errors. So Z plus or minus delta Z equals to A plus or minus delta A, which is measurement of one physical quantity, plus measurement of the other physical quantity will be B plus or minus delta B. Now, we know that Z is equals to A plus B. You can take the two factors out, which is A and B. So you can write that Z, which is equals to A plus B, Z, which is equals to A plus B. This implies what you get is delta Z is equals to delta A plus delta B. This is what you get the final result after you substitute where Z is equals to A plus B. Taking the two factors out, A plus B, they get cancelled on both the side, giving you delta Z equals to delta A plus delta B. So this is what you observe in case of a sum of errors. So what happens to the total error? The total error is the sum of the individual error. Now let's have a look at the next type of error, which is the combination using the difference in the error. Sum we just finished, where it is sum of the individual error. Now let's move on to the difference. Again, we have two such physical quantity A and B with the respective errors A plus or minus delta A and B plus or minus delta B. Now we consider the difference in the two physical quantity giving a new quantity Z. Next, what you do is make sure you apply those measurements. When you take measurements, there's a certain error that is introduced, which is given as this form, and this A plus or minus delta A and minus B plus or minus delta B. Okay. So next step, observe Z plus or minus delta Z equals to A minus B, and then you have A minus B, and then you have plus or minus delta A plus or minus delta B. A minus B, as we know, is nothing but Z. So eventually what you get is plus or minus delta Z is equals to plus or minus delta A plus or minus delta B. This is giving us the almost the same result as the previous case, where the total error, even by the difference in the two physical quantity, is sum of the individual errors. Again, let me repeat that one more time. The total error, even for a difference of two physical quantity, is the sum of the individual error. So we can make a note of this statement, where when two physical quantities are added or subtracted, the absolute error in the final result is the sum of the absolute error in the individual quantities. Just like what we observed for addition of two physical quantity and the difference in the two physical quantity, the errors summed up in both the cases. So when two physical quantity are added or subtracted, the absolute error in the final result is always the sum of the absolute error of individual quantities. Go ahead and make a note of this. I will anyways be sharing this PPT to you, so you can have a look at the statement one more time. Okay. Let's take a look at it by an example, so to get a better understanding. So the example here that I've used is temperature. Is the temperature of two bodies measured by a thermometer. Now you're using an instrument that is a thermometer, and thermometer also has certain resolution. So that resolution obviously will induce certain errors. So here the error, as you see for temperature T1, is 20 degrees Celsius plus or minus 0.5 degrees Celsius, and T2 is 50 degrees Celsius plus or minus 0.5 degrees Celsius. Calculate the temperature difference and the error therein. Calculate the temperature difference. First, we will write the things that are given. Given temperature T1 is 20 degrees Celsius plus or minus 0.5 degrees Celsius. T2 is 50 degrees Celsius plus or minus 0.5 degrees Celsius. Difference in the two is T, which is equals to T2 minus T1. That does not look like a T, so I will correct that and then write it as a T. T2 minus T1. You know the value for T2, you know the value for T1, but the problem is, what about their absolute errors? Remember, the absolute errors, delta T, which will be always equals to sum of the individual errors. Even though if it's a sum or a difference, the absolute error will always be sum of the individual error, which is delta T1 plus delta T2. You may ask the question, where is delta T1 in this particular statement? There is nowhere that I've mentioned delta T1. Well, it's understood that absolute error is always followed by a given value, which is nothing but the magnitude of temperature in this particular case. So this is basically your delta T2, and this is what you have as a delta T1. So we substitute where delta T equals to 0.5 plus 0.5. And what's 0.5 plus 0.5? 1.0 degree Celsius. Notice I have written 1.0 and not just 1, is because this is the resolution of a given instrument, which is 0.1. Resolution is up to 0.1, which is 1 decimal place. So this 1 decimal place is important for us. So we put a 0 to show that there is no number that exists, but still important for us to show that there's a resolution which is 1 decimal place. So now that we know delta T so much, so we can find where T2 is 50 minus 20. 50 minus 20 is 30, plus or minus delta T is 1.0 degree Celsius. This is how you identify a given physical quantity or the measurement of a physical quantity due to the combination of multiple measurements or combination of errors as well. All right. So one part is sum or difference. Can you guess what would be the other two parts? That's right, you guessed it right. It is the product and the quotient. So let's take a look at it. Suppose Z equals to A into B. So what you're trying to do here is multiply two different physical quantities. When you multiply two different physical quantity, you get a new physical quantity which is given by Z. So the measured values of A and B are A plus or minus delta A and B plus or minus delta B. Again, what is delta A and delta B? Let's write that one more time. Delta A and delta B are called absolute errors for a given quantity A and B only. For A, the absolute error is delta A. For B, the absolute error is delta B. Similarly, you can also write the absolute error for Z. What will be mentioned for Z? Delta Z. So let's write that down, where Z plus or minus delta Z, which is equals to A plus or minus delta A times, I am not adding, I am not subtracting, but rather multiplying, where A plus or minus delta A, B plus or minus delta B. Okay. Now that we have this, we multiply the two quantities that are within the bracket by using a distributive property. So go ahead and solve this with me, where you write Z plus or minus delta Z, which is equals to AB, then A delta B, but the sign is plus or minus, so I put plus or minus A delta B. Next, plus or minus delta A B, or let me write B delta A, and then you have plus or minus delta A delta B. So this is what you get after using the distributive property for these two given elements. You get this. After multiplying, you get this. Now, what you do next is divide both the sides by AB. Divide both sides. So I'm going to write BS. Don't assume it is something else. BS stands for, no, not what you think it is. It stands for both sides. Okay. In mathematics, both sides. Dividing both sides by AB. Okay. The left hand side as well as the right hand side. So let's go ahead, try to divide by AB. So I've already put that there. So, okay. So I'm going to divide both sides by AB. Z plus or minus divided by AB. Delta Z AB, which is equals to, go back, AB, AB by AB, AB by AB. So I need to keep going back and forth to have a look at the values. Plus or minus, or let me first write this down the next page and then I will divide it. Okay, I'll write this down once again in the next page and then I'll divide it, because it's hard for me to refer as well. It is difficult for me to refer. So delta plus or minus Z plus delta Z equals to AB plus or minus A delta B, A delta B, A delta B plus or minus B delta A, if I'm not mistaken. Yes. So you can check while I'm writing delta A and delta B. Correct? Now we divide both sides by AB. So now you get Z by AB plus or minus delta Z by AB, which is equals to AB by AB plus or minus A delta B by AB plus or minus B delta A by AB plus or minus delta plus or minus delta A delta B by AB. Now, from the previous section, you will see that Z is equals to AB. Z is equals to AB. So here, in place of AB, I can substitute Z. So Z by Z plus or minus delta Z by Z equals to AB cancels. So AB cancels. A and A cancels here. B and B cancels. In case of delta A, delta B, first of all, delta A, an absolute error for A, and delta B, absolute error for B, are very small quantities. Delta A, delta B are small quantities. And when you multiply these two small quantities, which are of decimals, what happens is that they become even smaller quantities. To give you an example, let's assume 1 by, let me change that color, 1 by 10 times 1 by 20. This is a small value which is about 0.1. This is also a small value which is about 0.5. Yeah, but what happens when you multiply each other? You get 1 by 200. That's even smaller quantities compared to these two. So when two small quantities such as the decimal values, when they are multiplied, you get even smaller quantity. Therefore, this value will be very small and negligible, so we can ignore. So what do? Ignore. We don't want it. Say bye-bye to it. So this last equation is gone. Bye-bye last equation. Now, the remaining, we write them down as delta B by B plus delta A by A. Plus or minus, plus or minus, plus or minus. I was almost about to forget that. You can cancel the Z here. Very good. And what you're left with is this given quantity where plus or minus delta Z by Z plus or minus delta B by B plus or minus delta A by A. This is a very familiar quantity which is called a relative error. A relative error is the ratio of absolute error to the measured value, ratio or the true value, ratio of absolute error divided by the true value. So you can finally write this equation. I'll put it here in a box. Delta Z by Z, which is equals to delta plus or minus delta A plus or minus delta B by A by B, relative error. So for both, for a product as well as for a quotient, you can work with the quotient. Go ahead, try your best with the quotient. You will see in both the cases that that the product or the quotient of two quantities, the error what you obtain is always the sum of the relative error. This is what is called a relative error, where you take the ratio of absolute error divided by the true value. So what you obtain as the combination for a product and a quotient is the sum of the relative error of individual physical quantity. So let's make note of this statement. Oh, I need to remove these. Okay, let's make note of the statement. When two quantities are multiplied or divided, the relative error, so here we look into the relative error, in the result is the sum of the relative error in the multipliers. Okay, it is always sum of the relative errors in the multipliers. Multipliers like those individual quantities like A and B. So what better way to understand than an example? Let's take a look at an example where we have to multiply or divide a given relative errors, where we have to find the combination of errors. Resistance R equals to V by I. You might have learned this in your 10th standard or in your 9th standard. If I'm not mistaken, it has to be in 10th, where you learn Ohm's law. And Ohm's law is defined as the ratio of voltage to the current. And this constant, what you get as a ratio of voltage and the current, is called the resistance of a given conductor. R equals to V by I. V is called the voltage, I is called the current, R is called the resistance of a conductor. Voltage has a certain value that is given to us, 100 plus or minus 5 volts, plus or minus 5. This 5 is the error. It could be added or it could be subtracted with 100. Similarly, current also is given with an error of plus or minus 0.2. Okay, so now we need to find what is the percentage of error in R. Percentage of error in R. First of all, when you use the given relation, which is R equals to V by I, we can identify the numbers 100 and 10, which gives you about 10 ohms, all right, which is equals to 10 ohms. That's because voltage is 100, current is 10, therefore you get 10 ohms. What about the error? To find the error, we write delta R by R, which is the relative error, times 100, because we're trying to find the percentage, which is equals to delta V by V times 100 plus delta I by I times 100. See what we're trying to determine here is the percentage of error. First we find the relative error and then we can find the percentage of error, which is times 100. So let's go ahead and try to solve this, where we find the percentage of error. So this is equivalent to writing of percentage of error in R. So percentage of error in R is equals to delta V by V. What is delta V? Delta V is the absolute error in the voltage. That is 5. 5 by true value is 100 times 100 plus delta I is 0.2 divided by 10, because true value is 10, times 100. Solve to find the percentage of error in R. Percentage of error in R, which is equals to, cancel these two, one of the zeros gets cancelled, and 0.2 times 10, shift the decimal place, which becomes 2. So I will write this 2. Now these are percentage. You have found the percentage. One is 5%, the other is 2%. 5% plus 2%, total of 7%. So percentage of error in R is 7%. What will be the total error? Well, you have to find delta R. I can show you in the next trick. This is not mentioned in the textbook, but you can go ahead, proceed with the next trick, which is to find the delta R. Why are we doing it? It's fun. So delta, percentage of error in R, which is equals to delta R by R times 100, which is equals to 7%. All right. Now R, as you know, we found it to be 10 times 100 equals to 7%. So 0, 0 cancels and you get this delta R, which is equals to 7 by 10, where delta R is equals to 0.7 ohms. You have found which is the absolute error for resistance. And now we can write here as plus or minus. Again, this is not part of the question. We're doing it because it is fun. I know some of you would disagree, but 0.7 ohms. Okay, plus or minus 0.7 ohms. But this is actually what we're supposed to find, but we've gone one step ahead in order to determine what would be the combination of error, meaning the absolute error in resistance. All right, so moving on. This is the same question. Okay. Moving on. What happens, it's not significant figures. One sec, we have not yet entered into significant figures. This is still combination of errors. What about errors which have raised to the power? Example is this: z equals to a square. A physical quantity whose power has been raised square. How would you find such an error? Nothing to worry. All that is meant here to do is understand that z is equals to a times a, which is equivalent of product of two errors. And what do we know about product of two errors? Is the sum of the individual absolute errors. So delta z will be sum of the absolute errors, which is delta, the relative sum of the individual relative errors, not just the absolute. Delta a by a plus delta a by a. Now you have delta a by a plus delta a by a, which is equals to 2 times delta a by a. If so is the case, what about a cube, where z equals to a cube? Well, if you work out this, again you will get where delta z, which is equals to 3 times delta a by a. So now you know what happens if the powers are raised to 4, 5, 6, 7. What happens to the relative error, the total relative error, which being the number that is raised to the power times the relative error of a given physical quantity. So let's take a look at this by another example. You have z equals to a to the power of p, b to the power of q, and divided by c to the power of r. What happens to the individual error? What happens to the relative error, the total error? Where you have delta z by z, which is equals to a to the power of p is written as p delta a by a, just like what we observed in a square is 2 times delta a by a. So a to the power of p is p times delta a by a, plus, since you're multiplying here, so your next is q delta b by b, and also division, which is still a plus r delta c by c. This is how you determine the total relative error, which is equals to the part which I've written towards the right hand side. Pretty lengthy one. Little hesitant to read that out. All right, so let's take a look at an example. Find the relative error in z if z equals to a to the power of 4, b to the power of 1 by 3, c and d to the power of 3 by 2. Simple. Try this by yourself, where you write delta z by z, which is equals to 4 times delta a by a, 1 plus 1 by 3 times delta b by b, plus 1 times, why is it 1 times? Because it's c to the power of 1 delta c by c, and plus 3 by 2 delta d by d. There you go. That is all. Okay. Let's look into a practical perspective. You can go ahead and try to read it out. It says the period of oscillation of simple pendulum is t equals to 2 pi square root L by G. Measured value of L is 20 centimeter, known to 1 millimeter accuracy, and the time for 100 oscillation of a pendulum is found to be 90 seconds using a wristwatch of 1 second resolution. What is the accuracy in determination of G? So let's take this given equation, which is T is equals to 2 pi square root of L by G, and try to equate it to G. So to equate it to G, first you have to transpose that 2 pi. So you get T by 2 pi is equals to square root of L by G. Square on both the sides. By squaring on both the sides, you get T square by 4 pi square. And why is it 4 pi square? Because square of 2 is 4 and pi square, as it is equals to L by G. What do I equate it to? I equate it to G. And you write G, which is equals to L by 4 pi square, no, L times 4 pi square, L times 4 pi square divided by T square. Okay, so I've moved that to the numerator there and that to the denominator, and this is what you get. Okay, keep this in the box. We're going to use this where G is equals to 4 pi square L by T square. We know that L is given, which is 20.0 plus or minus, the accuracy is 1 millimeter. 1 millimeter in terms of centimeter is 0.1 centimeter. Okay. T is also given 90 plus or minus, resolution is 1 second. So now we need to first find what error, how much would be the error in G. Since you're dividing the two, L and T square, let's not worry about the numbers. When it comes to determining the errors, don't worry about the numbers which are constant, such as 4 and pi square. Not to worry. The variables L and T square is what you need to be concerned about. So first, to find that error, delta G by G, which is equals to L is 0.1 divided, let me take you step by step. Let me not do that. I'll take you step by step. Delta L by L, the error, the relative error in the length, plus, why is it plus? Because it's dividing L by T square, division, quotient, meaning sum of the relative errors. So 2 times delta T by T. Delta L is 0.1 and L value is 20 plus 2 times delta t is 1 divided by 90. Okay, so make a note of this. I will be moving on to the next slide, so I don't have space here to solve. Okay, so I'm going to determine this accuracy in terms of a given percentage. So I'm going to multiply it with 100. So 0.1 divided by 20 times 100 plus 2 times, I'm trying to recap, is 1 by 90 times 100. There you go. I did it. Okay. And what you get? Delta G by G times 100, which is equals to, cancel one of the, all right, and then you get 1 by 2 plus 0, 0 you can cancel, and then you get 20 by 9. 20 by 9, if I'm not mistaken, 20 by 9 must be equals to 2.22222222. So I'll just put it to 2.22 since my resolution is just about 1. So, all right. So next you get 2.57, which is your percentage of error. 2.57, 20, yes, 20 by 9. All right, and then you can find that the accuracy comes down to, if I'm not mistaken, about 25.7. So you can take a look at it, but this is how you obtain the given number 2.57. So don't worry about the accuracy, we'll come to the accuracy. 2.772. Okay. One moment. A quick correction. 2.72. 2.72. That is what it comes down to, not 2.5 and 2.72. Quick correction there. Okay. So this is how you can find the accuracy in determination of the value G. All right. So we're starting with significant figures. Now that we're running short of time, I thought maybe we could start with significant figures. Nevertheless, we shall start this in the next class about significant figures. I'll have, this was a quick rules and things that we were about to discuss. But anyways, not to worry, just follow us on www.we-learning to get more details about the class. I'll catch up with you in the next class. Until then, everyone, take care and have a nice day. Bye bye all.